Have you ever looked up at the night sky and felt a sense of wonder? We've all gazed at the stars and pondered our place in the vast expanse of space. For centuries, humans have used the stars to navigate, to explore, and to understand our world. Today, we have a tool that connects us to those same celestial bodies in a whole new way, the Global Positioning System, or GPS. GPS is more than just a way to find your way home. It's a revolutionary technology that has transformed the way we live, work, and explore. It allows us to pinpoint our location on Earth with remarkable accuracy. Whether you're driving, hiking, or even just checking the weather on your phone, chances are you're using GPS. But how does this incredible system work? The answer lies in a delicate dance between space and time, signals and calculations. It all starts with a constellation of satellites orbiting our planet, each broadcasting its own unique message. By decoding these signals, our GPS receivers can determine their distance from multiple satellites. This information, combined with some impressive geometry, allows us to determine our precise location on Earth. It's a testament to human ingenuity and our relentless pursuit of knowledge. So buckle up as we embark on a journey to uncover the secrets of this modern marvel. Imagine a network of eyes in the sky, constantly watching over us, sending down invisible beams of information. That's the essence of the GPS space segment. This segment consists of a constellation of approximately 30 satellites orbiting Earth at an altitude of about 20,200 kilometers. These satellites aren't just randomly scattered across the sky. They are strategically positioned in 6 orbital planes, ensuring that at least 4 satellites are visible from almost any point on Earth at any given time. This redundancy is crucial for accurate positioning. Each GPS satellite acts as a precise timekeeper, carrying multiple atomic clocks that measure time with incredible accuracy. These clocks are synchronized with each other and with ground-based clocks. This synchronization is vital because the entire GPS system relies on the principle of time of flight. As these satellites orbit Earth, they continuously transmit radio signals containing information about their position and the current time. These signals travel at the speed of light, reaching our GPS receivers on the ground. By analyzing the time it takes for these signals to arrive, our receivers can calculate the distance to each satellite. While the space segment provides the raw data, it's the control segment that acts as the brains of the entire GPS operation. This segment is responsible for monitoring the satellites, ensuring the accuracy of their clocks, and updating their orbital information. The control segment consists of a global network of ground stations, including a master control station, monitor stations, and ground antennas. These stations are strategically located around the world to maintain continuous communication with the satellites. The Master Control Station, located at Schriever Air Force Base in Colorado, USA, is the heart of the control segment. It receives data from the monitor stations, which track the satellite's positions and clock performance. This data is then used to generate precise orbital information and clock corrections for each satellite. The ground antennas transmit these updates to the satellites, ensuring that they maintain their precise orbits and that their clocks remain synchronized. This constant monitoring and adjustment are essential for maintaining the accuracy of the entire GPS system. The final piece of the GPS puzzle is the user segment, which includes all of us. This segment encompasses any device that receives and interprets the signals transmitted by the GPS satellites. This includes everything from dedicated GPS navigation devices to smartphones, cars, and even wristwatches. GPS receivers are designed to capture the radio signals transmitted by the satellites. These signals contain information about the satellite's position, its clock time, and the health of the satellite. The receiver then uses this information to calculate its own position. To determine its location, a GPS receiver needs to receive signals from at least 4 satellites. This is because each satellite provides a single measurement, the distance between the satellite and the receiver. By combining the distance measurements from multiple satellites, the receiver can triangulate its position in 3-dimensional space. The accuracy of a GPS receiver's position estimate depends on several factors, including the number of satellites in view, the geometry of the satellites, and atmospheric conditions. However, modern GPS receivers can achieve remarkable accuracy, often within a few meters of their actual location. Section 5. Signals from space. How GPS determines your location. Imagine you're standing in a park and you hear the faint sound of music. As you walk towards the music, it gets louder. If you had friends positioned around the park, each playing the same song, you could use the volume of each friend's music to estimate your distance from them. GPS works in a similar way, but instead of sound, it uses radio waves. Each GPS satellite transmits radio signals at a specific frequency. These signals travel at the speed of light and contain information about the satellite's position and the current time. When a GPS receiver on Earth picks up these signals, it measures the time it took for the signals to travel from the satellite to the receiver. Because the speed of light is constant, the receiver can calculate the distance to the satellite using this time difference. For example, if the receiver's clock is perfectly synchronized with the satellite's clock, and it takes 0.067 seconds for the signal to travel from the satellite to the receiver, then the distance between them is approximately 20,100 kilometers, which is 0.067 seconds times 300,000 kilometers per second. Section 6. Triangulation in 3 dimensions. The power of trilateration. Now, imagine you have 3 friends standing in a triangle around you, each holding a string attached to your wrist. By measuring the length of each string, you could determine your exact position within that triangle. This process is called triangulation. GPS takes this concept to the next level with trilateration. Instead of friends and strings, we have satellites and radio signals. By measuring the distance to at least 4 GPS satellites, a receiver can determine its position in 3-dimensional space. Each distance measurement from a satellite creates a sphere, with the satellite at the center and the radius equal to the calculated distance. The receiver's location lies somewhere on the surface of that sphere. By combining the distance measurements from multiple satellites, we get multiple spheres that intersect at a single point. This point represents the receiver's location. With 4 satellites, we can determine latitude, longitude, and altitude. This process of trilateration is the foundation of GPS positioning. It allows us to pinpoint our location on Earth with remarkable accuracy, using nothing more than signals from space. Section 7. The limits of precision. Factors affecting GPS accuracy. While GPS is incredibly accurate, it's not perfect. Several factors can affect the accuracy of GPS signals and therefore the accuracy of our position estimates. Understanding these factors is important for interpreting GPS data and ensuring reliable navigation. One significant factor is the Earth's atmosphere. As GPS signals pass through the atmosphere, they encounter varying densities of charged particles. These particles can delay or deflect the signals, introducing errors in the distance measurements. Another factor is signal blockage. Tall buildings, dense forests, and even mountains can obstruct GPS signals, preventing receivers from obtaining a clear line of sight to the satellites. This is particularly problematic in urban canyons and mountainous terrain. The geometry of the satellites can also impact accuracy. When the satellites are clustered together in the sky, the intersection of the distance spheres becomes less precise. This is known as a poor geometric dilution of precision, GDOP. Other factors that can affect GPS accuracy include receiver clock errors, satellite ephemeris errors, inaccuracies in the predicted satellite positions, and even space weather events like solar flares. Section 8. A world of navigation exploring GPS alternatives. While GPS is the most widely known global navigation satellite system, it's not the only one. Several other countries and regions have developed or are developing their own GNSS, each with its own constellation of satellites and unique characteristics. Russia's GLONASS, or Global Navigation Satellite System, is a fully operational GNSS with global coverage. It uses a different orbital configuration than GPS, with satellites orbiting in 3 orbital planes instead of 6. The European Union's Galileo is another GNSS that is nearing full operational capability. Galileo aims to provide more accurate positioning and improved performance in challenging environments compared to GPS. China's BeiDou navigation satellite system is a rapidly expanding GNSS with a growing number of satellites. BeiDou offers both regional and global coverage and is becoming increasingly popular in Asia-Pacific regions. India's Navi-C, or Navigation with Indian Constellation, is a regional GNSS that provides positioning services over India and its surrounding areas. Navi-C is designed to provide reliable navigation for both civilian and military applications. These alternative GNSS offer several advantages, including increased redundancy, improved accuracy in certain regions, and reduced reliance on a single system. Section 9. From paper maps to pinpoint accuracy, GPS in the modern world. GPS has revolutionized the way we navigate and interact with the world around us. What was once the domain of explorers and adventurers is now an integral part of our daily lives. From finding our way home to tracking packages, GPS has become an indispensable tool. In transportation, GPS has transformed everything from car navigation to air traffic control. It has made driving easier and safer, reduced traffic congestion, and improved the efficiency of logistics and shipping. In aviation, GPS provides precise navigation for aircraft, enabling safer landings, more efficient flight paths, and reduced fuel consumption. It has also enabled the development of unmanned aerial vehicles, or drones, which are increasingly used for various applications. GPS plays a crucial role in emergency response, allowing first responders to locate victims quickly, coordinate rescue efforts, and deliver aid to those in need. It has also become an essential tool for search and rescue operations in remote areas. Beyond navigation, GPS has enabled countless other applications, including precision agriculture, where farmers use GPS to guide tractors, optimize planting and fertilization, and monitor crop health. Geotagging, where photographers and social media users use GPS to tag photos and videos with location information. And scientific research, where scientists use GPS to track wildlife, monitor earthquakes, and study climate change. As technology continues to advance, we can expect even more innovative uses for GPS in the future.